Thanks a lot.
Thank you. Good afternoon. This talk will summarize some stress parameter variability work that Walt and Nick Greger and I have been doing. So we're trying to shed some light on the inter-event parametric terms and specifically on stress parameter as a function of depth. Now, why are we looking at stress parameter? For two reasons. One, it's a robust descriptor of high-frequency source scaling. And two, it's a convenient single parameter estimate of source variability, or sigma. It's a very simple parameter, and it's also very easy to estimate. Now, how do we get at stress parameter? Oops. We do it typically by inverting Fourier amplitude spectra. And once you have the Fourier amplitude spectra, you can get this from either strong motion data, weak motion data, or from ground motion prediction equations. Then you just run it through an inversion code. We can invert for kappa as well as stress parameter. We can also invert for magnitude. We can also have different psi terms. We can usually invert for both soil and rock, but we can invert for any number of terms that we want. One of the key things in the inversion is to incorporate site and crustal amplification factors in the inversion. If you don't do that, you end up getting quite high stress parameters, but basically the sigma, the scatter in the estimates with or without crustal amplification will be quite similar. And we recommend using multiple approaches, and I'll show examples of both of those in this talk, one using recorded data and one using ground motion prediction equations. So we're going to look at the NGA data set, and we've added 5 earthquakes to it, and we've excluded 5 Chi-Chi aftershocks and the Cape Mendocino main shock from the data set. So basically, it's still the NGA data set without Chi-Chi and Cape Mendocino. Cape Mendocino was excluded because it's an offshore California earthquake and probably associated with subduction in Northern California. So this is the NGA data set, and part of the metadata, we're going to look at, in this study, magnitude, mechanism. For you not familiar with the NGA data criteria, 0 will mean strike slip, and 3 will be like reverse oblique, and 2 I think is reverse, and 2 is reverse, and 1 is normal, and 4 is normal oblique. And we're also going to look at the top of rupture, and the final parameter on the far side is the stress parameter. I'm going to just go through this quickly since we're in Northern California. We're going to look at the Northern California events. The first one is first one is Coyote Lake. Oops, wrong way. And it's a strike slip event, magnitude 5 3/4, and it's a deep slip. Even though there's some surface rupture, most of the slip occurred at deep from the slip models. So the top of rupture is 3 kilometers. And the stress parameter is somewhere in the 50s. Looking on the next page, where is it? Loma Prieta should be on this page. It's a deep event, magnitude about 7. Stress parameter will be lower in the, I can't see it, on the 20s or 30s. And the top of rupture is about 3.8 kilometers. Then we're looking at down here, Parkfield and San Simeon, 2 more recent Northern California events, both shallow rupture, top of rupture 0.5 and 2, and again the stress parameter is going to be somewhere in the 20s and 30s. I should define how we define slip depth. We define it shallow slip depth if we look at an inversion from a rupture model, and it looks like, well, 20% or more of the slip occurs in the top 5 kilometers. It's deep slip if 20% or more of the slip occurs, 80% or more of the slip occurs deeper than 5 kilometers. So even with the large NGA data set, you notice there are only 6 earthquakes in Northern California, and partially because of that, we're only looking at the ones with stress parameters. If you go back, we don't have stress parameters for the bulk of the NGA data set, and that's because finite rupture models have not been done for a large number of these earthquakes, especially the early earthquakes, because they were basically because a lot they were sparsely recorded, and because there's just not enough grad students anymore. So how does stress parameter variability in Eastern North America, which is really what we want to get out to, compare with Western North America? And one of the main parts of the project ongoing is we're going to look at small magnitude stress parameter variability. And if they're similar, this may suggest comparable source variability between Eastern North America and Western North America. But that's the subject of ongoing study and what a lot of the NGA East will be done. But we can look at what we have for large magnitudes. And this is from the NGA earthquakes, and we have 24 earthquakes, including both deep slip and shallow slip, for which we have stress parameter estimates. And the stress parameter is about 30 bars, and the sigma is about 0.6. Now, what do we have in the East? Now, this is actually taken from some work Ken Campbell did. Oops. So these are the eastern earthquakes from Nahanni to Saguenay, which has very large stress parameter estimates, no matter which way you estimate it, down through some small earthquakes. You'll notice in the east, there's a lot more magnitude 4s in here. In the west, we're dealing more with magnitude 5s to 7s. And here, Walt has estimated if you include Saguenay in the estimate of stress parameter, you get roughly 60 bars, but a very large natural log, sigma natural log of almost 1. If you take out Saguenay, of course, you're going to drop down, and your sigma is about 0.42, which is closer to, more comparable to the Western estimate. But depending on how many stations you add here, you'll be able to get nearly any sigma you want between 0.42 and 0.98. So one of the key things as we move on is, how are we going to treat Saguenay? Is it an outlier in our distribution, or do we need to include it? And that's one thing that we hope the small magnitudes can give us some additional guidance on. So for large magnitude, it depends, of course, on your treatment of Saguenay, and hopefully the results of the small magnitude study will help us figure out how to treat Saguenay in this context. Okay. Now we're going to look at some Western magnitude stress parameter observations. Some of these have been well known for a long time. Oops, wrong buttons. They generally decrease as magnitude increases. They vary with fault mechanism. Generally normal is less than strike slip, is less than reverse. And the more recent one that Walt started to look at in 1996 is that it increases as slip depth increases. That's one reason I spent some time with the NGA data set looking at top of rupture and stuff. If you remember, for the ones with top of rupture with deep, most of the stress parameters around 50 bars in the 50s, and if you had shallow, they were between 20 and 35 bars with quite a bit more scatter. So again, shallow slip, to remind you, is 20% more of the moment released in the top 5 kilometers. So Western, and we hope Eastern, stress parameter variability can be reduced by a combination of epistemic components. Now, typically, everyone in the ground motion prediction equation includes magnitude, but also you want to include, fault mechanism, and the one we're going to spend most of the time on is slip depth. Okay, now, this is a bit more complicated slide. This shows the top third, shows an inversion for both soil and rock sites. We're looking at 3 magnitudes, 5.5, 6.5, and 7.5. 3 styles of faulting: strike slip, normal, and reverse. And if you look for each style faulting, the stress parameter decreases as magnitude increases. So that's not a new result. We're trying to show this to show that we can replicate the classic results, such as stress parameter decreasing with magnitude, to give us a bit more confidence that what we're seeing down here, and this is for rock sites only, we haven't completed the rock and soil site inversion, but between shallow and deep is also a real effect. And if you look at the difference between shallow and deep, you'll notice that the deep in this column, and we define deep slip for the point source inversions as slip occurring below 6.8 kilometers, and shallow is basically slip at the surface. We always consistently have the deep stress parameters always greater than the shallow stress parameters for the three fault types: strike slip, normal, and reverse in this case. And you also notice the same trends you see before is that, depending which column you look at, shallow, normal, strike slip is usually a little bit bigger than normal, but not usually significantly so. But reverse over here will be significantly, maybe 20% bigger than strike slip. And you also see those trends up there. All right. So now we're going to look at the NGA data, augmented NGA database that had 24 earthquakes with stress parameters. Of those, 18 were shallow and 6 were deep. And you saw this slide before. So the stress parameter for all 24 was roughly 30 bars, with a sigma of 0.6. For shallow, which is the bulk of the earthquakes, we have 18 earthquakes, and the stress parameter is a little reduced, and the sigmas are comparable. But for the deep earthquakes, which we only have 6, 2 of which were in Northern California, which were Coyote Lake and Loma Prieta, and then the rest are in Southern California, particularly Whittier and San Fernando, a couple others. The stress parameter is quite a bit higher, basically almost doubled, and the sigmas are significantly lower. So looking back at what Norman saw when he had his plot up of JB distances with very different depths, we see a large factor 2 increase with stress parameters with depth. And that may help explain some of what Norm was seeing in his earlier work. But even more significantly for this study, a huge, factor 3 decrease in variability. And I just want to point out, one reason we need more work, this is a small number of data points. And, we're in Northern California where we go back, we have earthquakes for a long time. In Central and Eastern North America, it's going to be a long time before we get equivalent number of data points. Okay, now this shows the slide stress parameter plotted versus magnitude. And this is for the 24 earthquakes. So if you're in shallow slip, it's an X. And if you have deep slip, it's the plus sign. And you'll notice that there is some magnitude dependence here. Most of the deeper slips, the biggest one is here is Loma Prieta, a little bit less than 7. And the smallest is Coyote Lake, which is this one right here. But most of the stress parameter estimates are 50 bars, plus or minus, not very many. Whereas there's quite a bit more scatter in the shallow stress parameter estimates. And you do see a trend that we see in the ground motion prediction equations that there appears to be a decrease with depth, which you also see in the ground motion prediction equations, which are based on a much larger data set. Again, this is only 24 earthquakes out of the NGA data set, which is close to 160 or 180. So you do see that trend. So we do see that in this data, which gives us a bit more confidence in the next slide, which is the most intriguing slide. Here, we're plotting versus top of rupture. So everything down here is shallow, and you see ranges from about 8 bars up to in the 50 bars with quite a bit of scatter in the stress parameter estimates for shallow earthquakes. And here you have the data for the deep. This one out here is Whittier and Narrows, and 2 of these are from Northern California, the rest are from Southern California. But you see very tight, right around 50 bars estimate for stress parameters from deep earthquakes. And that's one of the tantalizing things we're hoping to be able to look at is if we can separate out this effect, we can have an increase in your sigma, because currently some of the some epistemic sigma is perhaps masquerading as aleatory sigma. And this is an interesting preliminary result. We hope to get more data and also look at the small magnitude data in the East to help us with that. So with that, I'd like to thank you for your attention. You're welcome.
Okay, questions for Bob? Any question for Bob? No question. Okay.
They want an early break.